Okay, so in this session, we will begin Bernstein Vazirani algorithm, and I will explain how what is a problem that this algorithm solves. And even though its circuit looks almost the same as that of Dietz-Joza algorithm, I will show why it's very different, and it shows the power of quantum computer in a different way than a Dietz-Joza algorithm. And then we will, of course, have an implementation on Qiskit after this analytical work. So let me start by sharing my OneNote. Perfect. So let's begin. And hopefully, this is going to be less intimidating for you after having gone through Dietz-Joza algorithm. So we begin Bernstein Vazirani algorithm. And let's first discuss the problem that this algorithm solves. And the problem is this. Suppose you have a black box that implements an f of x such that whatever is the input bit string, it's given at the output a sum. So, and it has a secret bit string s. So this f of x essentially multiplies this x bit string with s bit string and find its dot product modulo 2. Okay, and that's what it gives out on this single output line. So this is again, this implements a function f of x from an n bit input to a 1-bit output. And that 1-bit output is the product, it's the inner product essentially of this input bit string x and a secret bit string s and of under modulo 2. Let me give you an example. Okay, suppose the bit string is 101. This is a secret bit string, and this is fixed. For a given black box, it is a fixed constant bit string. This x is input, and you have access to input, and x you can change. Okay, x could be anything. So your x could be 00, 001, 010, and you get all the way to 111. So what this black box does, that there is a function f of x, which takes this product x dot s, and let's suppose you have input 101. Okay, so this could be a little bit confusing. So let me start with an input. Let's say this 001. So suppose x is 001. So then this x dot s, which is nothing but s2 x2 plus s1 x1 plus s naught x naught, where this is s2 s1 s naught. So this 1 is s naught, 0 is s1, 1 is s2. And similarly, this x can be thought of as x naught, x1, x2. So this multiplies them with each other. So if x is 001, so this product and this sum would look like 1 into 1, 1, 0 into 0, 0 into 1, 0, and this is equal to 1. So in this case, this f of 01 is 1. Now suppose if x is equal to 010, so then f of x is equal to 0, into 1, 0, plus 1 into 0, 0, 0 into 1, 0 equals 0. If x is equal to 1, 1, 1, so then f of x is, so s was, let me write it again here, 1, 0, 1. So 1 into 1, 1, 0 into 1, 0, 1 into 1, 1. So 1 plus 0 plus 1 is 2, and modulo 2, it is 0, and so on. So this implements a function f of x that multiplies the input bit string with a secret bit string and gives the result out at the output. And the problem is, what is this s? So this is a problem that we have to solve. We have to guess the secret bit string present inside the black box. And this is Bernstein Vazirani problem. Now let's think about the classical solution. Suppose the black box has n inputs. So it means the string is also n bit long. So there is Sn minus 1, Sn minus 2, all the way to S0. So output is only 1. So to find out this bit string, what you do, you first give x is equal to 0, 0. Then what will happen, since all of these are actually, you don't even need to start with 0, because this is definitely result would be 0. You start with 0, 0, 1, and then the result would be f of x would be nothing but S0, because this S0 into 1 will give me S0, and then all other bits will multiply with this thing and they will be 0. So at the output, from the output, I will be able to see what is S0. So in the next input, you give 0, 0, all the way to 1, 0. Now then f of x would be simply this S1, because S1 into 1 is 1, S1, and all other inputs are 0. So the output will only depend on S1, and so on with n outputs. After n queries of this black box, you will be able to find what is this secret bit string. So this is the classical solution. Is everybody okay with this solution? Is able to understand? Ubaidullah, are you able to understand this problem and its classical solution? So Ubaidullah, yes. Okay, perfect. And what about Samin?
Excuse me, sir. सर ये इंक्वायरीज तो तब होगी ना जब हमारे पास सिर्फ एक ही वन होगा जो प्रोपेगेट होगा फ्रॉम द लास्ट पोजीशन टू द फर्स्ट प्लेस, तब इंक्वायरीज होगी। अगर बहुत सारे वंस हो तो फिर क्यूरीज बढ़ नहीं जाएगी क्लासिकल के केस?
No, because there are only n bits in this secret string. If there's this n input string, so we can sample each of the bit by giving inputs judicially. We don't have to give arbitrary inputs. Okay, we can select inputs judicially, because we know the problem. What problem are we going to solve? We have to find these bits of this secret bit string. So if we just give 1 in this at say last place and 0 everywhere else, the product will only be S0. So at the output, there will be S0 and I will have access to S0.
ठीक है, मतलब अगर 1 के साथ दूसरा भी 1 हो करीबी, इट्स लाइक जो
Okay, so if you give this input, so 0, 0, 1, then of course this is going to be S0 plus S1, but it means you're trying to solve this problem without trying to understand the problem itself. The problem is that I have to find this bit string, and I know f of x multiplies each bit string, each bit of the input with the corresponding bit. So why do I give this input anyway? It's not that I have to give every possible input. I should only give every possible input if I have a lot of time and computational resources at my disposal. For example, if this n is 100, and if I judicially select this placement of 1, I can solve this problem in 100 queries. And if you know are going to give all possible inputs, then you are going to spend 2 power 100, which is the trillions of trillions of trillions of queries of this black box.
ठीक ठीक
Okay,
ठीक है,
so
समझ गया.
we will make it 0 so that this doesn't show up. So this is not a blind method. This is a method that will work perfectly for this problem, and this is the most efficient way. You perhaps cannot come up with a way which will solve it better than this classical problem. Okay,
ठीक.
perfect. So classically you have to make n queries of the black box. So this problem is still, I would say better than the Diaz-Souza problem. In Diaz-Souza problem, you were supposed to separate and tell us if f of x that is implemented in the black box is either a constant or a balanced function. And there we saw that the worst case is exponential in n. Like more precisely, you can say 2 power n minus 1, but forget, that n minus 1 and these things, it's exponential in n, because 2 power 99 and 2 power 100 doesn't really matter much, right? So, but that was exponential, but this is only, n QEs. So classically, only n QEs are needed. Let's see the quantum mechanical problem, quantum mechanical solution. So Bernstein Vazirani recognized that this problem can be solved efficiently on a quantum computer by actually using this circuit, which looks amazingly similar to the Diaz-Souza algorithm, that you start all qubits in 0 state, and then you perform this Hadamard transform, and then you implement this function f in a phase oracle. Okay, and I hope that understand that in phase oracle this function doesn't appear at the output, but it appears like this, that this input x is transformed to -1 power f of x. So you implement this function f in a phase oracle, and then you apply this phase oracle to, after this Hadamard transform, then you apply this Hadamard again. And then you do this measurement. And the claim is that the end of the measurement on my classical bits, I will have that secret bit string right on the output. So whatever is the output is the classical bit string. That's the claim. I mean, so let me actually make a big screen, which means that if I plot my histogram after running this algorithm on a quantum computer, if let's say it's a 3-bit input, so for 0 0 0, for 0 0 1 0 1 0 0 1 1 1 0 0 1 0 1 1 1 0 1 1 1. So if the secret bit string is 101, my output will only have this present in the output, and everything else would be 0. That's our claim, that this will come with a probability of 100%. So it means when you run this algorithm, whatever is the output is your secret bit string, which means that on a quantum computer, you can do this in a single query. Okay, so this is faster. This is polynomially faster than the classical algorithm. And the question is that, and this algorithm actually came after Diaz-Souza algorithm. So why did people need this algorithm to really prove that quantum computer can solve some problem much faster than a classical computer, when already the result of Diaz-Souza algorithm was there, which actually shows that you can solve some problem exponentially faster than the classical computer. Can any one of you guess? If not, let me revisit Tide's Joza classical solution. So quantum mechanical, okay, is already there. So we know that it can be done in n is equal to 1. So to get exact solution, that is to tell if f of x is constant or balanced with 100% confidence or probability, we needed operations of the order of 2 power n minus 1. That's okay. But let's say if we have access to another classical computer, this is a deterministic Turing machine, or you can say the usual universal Turing machine or Turing computer, or just if you not familiar with Turing word, just think about it's a deterministic classical computer. Then this is what it is. But if you have access to classical random computer, it's classical, but it has randomness in it, which essentially mean that you can generate random numbers, perfect random numbers that doesn't have any correlation with each other. Okay, man, I'm not going to the details of what a random number is, but intuitively you can say that if you are generating random numbers from some process that you cannot predict what is coming later on, that's a true random number, so to say. So if you have access to a random number generator, then let's go back to that function again. So it has these n bit input and it has one output. So let's say you randomly select x and you give it as an input here, and of course you will get either 0 or 1, right? So for the sake of argument, let's say you get 0. What is the probability with which confidence or probability can you say the function f is a constant or balanced? 0, right? Because there's no way for us to tell us a function is a constant and balanced just because of one input, because one input could be anything. It could be 0 or 1, it doesn't matter. But let's say I choose another x for k2. Let's say this is for k1. K1 mean the number of executions. Now at the second step, as a second iteration of my program, I choose x randomly again. Okay, and I give it input here. And suppose I get output 0 again. So my first output was 0 and second output was 0 again. Now I can start formulating my answer in probabilistic term. That I can say that at this stage, when I get a second 0, that my with the 50% confidence, with let's say a probability of half, that this is not a balanced function, because when when this first 0 over here, I couldn't say anything, because it could be balanced or constant. I'm still at the same position as I was before I had done anything. But now after the second iteration, I can say with some confidence that this is probably a balanced function, a constant function. And let's say I select another random input, and then I give this to it, and I get a 0 again. Now my probability of saying that this is a constant function has increased, because for 3 inputs I have been able to get it the same output. So actually, technically, I can compute this probability to like this. So this is because this 1/2 is the probability each time coming for 0 and 1. But then there was half probability after this. There was half probability for this to come, and then another half probability for this to come, and half into half is 1/4. So 1 minus 1/4, which is essentially 1 minus 1/4, 3/4. So with 3/4 confidence, I can say that this is a constant function. And let's say I choose another x randomly and then give it here. Then, and suppose it comes 0 again. Now, again, my confidence in saying that this is implementing a constant function has increased, and now it is 1/2 power 3. So even if you don't, for now agree on this number, you can get this general idea that by access to a random number generator, I can solve this problem much more efficiently on a classical computer if I'm just looking for a probabilistic answer and not the exact answer. And I can increase my confidence in the answer by simply increasing the number of iteration in it. So it means that after this k iteration, the probability of me getting a correct answer has increased to this 1/2 minus k, which is exponential in k. So this problem can be efficiently solved on a probabilistic classical computer. So of course, it still cannot be solved in one iteration, but hey, if you have this 100-bit input, if you can get a pretty good idea by giving, let's say 10, by making only 10 iteration or 15 iteration, and 10 and 15 iteration, means what? With 15 iteration, your probability, your confidence is like 1 minus 1/2/14, which is nearly 1. So this Dietz-Sosa problem can be, sort of efficiently solved on a probabilistic classical computer. So in the first, sort of view, it seems like an exponential speed up over classical computer when we go to quantum computer. But when we really analyze it, then we say that, okay, now we see that the advantage in quantum computer is really not that great. Okay, but even though there's one big thing, if we are looking for exact answer, then of course quantum computer is exponentially better than classical computer for Dietz-Sosa algorithm. But if we are content with, let's say, saying that I can say with 99.9999% confidence this is a constant or a balanced function, then it is not a big difference between a classical computer and a quantum computer. However, let me now go back to this, Bernstein Vazirani problem, that why this is important. So over here, the quantum computer solution scales as is given by a single Curie of this black box, but a classical solution is given by n Curies, and there is no as yet known probabilistic quantum classical algorithm that can give us results faster than this n Curies. So this separation or this sort of difference in two computers is actually much more profound than what was shown by the Dietz-Sosa algorithm. At least if we are ready to consider probabilistic classical computer in the classical realm. Okay. Is everybody okay? Why we are studying Bernstein-Vazirani problem even after establishing Dietz-Sosa, algorithm that we can get a quantum speed up. This is this online teaching is really sort of bad thing that I'm concentrating on the screen and I wasn't even able to see the chat. Now I see that somebody is saying yes, so that means at least 1% and 2%, okay, understand that there is a reason to study Bernstein-Vazirani problem. So if you all agree now that this is a worthwhile problem. Let's now go and analyze the circuit, because I have just so far given the claim and not the proof that this quantum computer, this quantum algorithm can solve this problem in one iteration. So that's what I'm going to do now. Okay, so Bernstein Vazirani algorithm, and let's analyze this algorithm. Fortunately, we have almost everything that we need for this algorithm from the Dirac algorithm, because it looks very similar. So I'll be using some of the mathematics that we developed in the last lecture. So just to reiterate, we have inputs initialized to 0 state. And by the way, let me give an abbreviated representation. So sometimes people, just write it like this. You can say this is this phase oracle. These are n bit quantum register that is going on. And even for this, Hadamard, I can write Hadamard over n qubits, and then Hadamard over n, and then measurements. So this is the schematic of this algorithm. So let's start from here. So let me call the state here psi naught, state here psi 1, state here psi 2. As always, this is a bit easier, and then the result over here, whatever. Let's just call it y. Okay, so psi naught, as we saw yesterday, is this tensor state of all qubits in 0 state, and psi 1 is nothing but Hadamard on each of these states, individual qubits. And we have already seen yesterday that this is essentially nothing but 1 over capital N and a combination of all possible basis state, which I can symbolically write. This n is nothing but 2 power n. X goes from 0 to n minus 1, and this is just x, where this x is a label which is equal to the decimal value of the bit string given over here. So for example, for this, x is equal to n minus 1, capital N minus 1. Okay, so this is the Hadamard transformed input. And now let's define our phase oracle. So psi 2 is what we get after passing the circuit state through this phase oracle UF. And the phase oracle this time is actually this. Let me first, write it like this. So this UF passes on to each of this cut state UF X. Now, this UF is just this, that whatever f of x is implemented goes to the phase of -1 and multiplies with the input. But this time our f of x is s dot x. By the way, I'm writing this s vector dot x vector just to emphasize that this is a bit string and this is a bit string, and this is almost like that dot product of two vector, where you can think of different bits as different components. And some people would just write this as s dot x, and some other people might have some other notation. Anyway, so this is how I am dealing with it. So this becomes psi 2 as 1 over n square root x minus 1 power s dot x over x. Now come the last Hadamard transform. So we have reached this part. So over here, the state is psi3. So psi3 is after this Hadamard transform of psi2, which is n square root x minus 1 power s dot x Hadamard of x. Now this is that general Hadamard transform that we studied last time. So I'm going to use that result. So 1 over n square root sum over x minus 1 power s dot x, and then there's 1 over n square root sum over k from 0 to n minus 1 minus 1 power x dot k and k. Okay, so this is the substitution for the Hadamard transform of this general state x. So this x could be 0 state because this is a sum over x where x is going from 0 to n minus 1. So x could be 0, x could be 1, x could be 2, x could be 3, and so on. And each of its transform is given by this, and this transform, as you can see, depends on x because this x dot k appears in minus 1 power this. And but this is another sum over k. Okay, so let me now write it in a rearranged form. This n square root and n square root multiplies together to make 1, to make n. So let me bring this sum out, k0 to n minus 1, and keep everything over here and this k over here, because this k state is changing. This is for 0, 0, 0, then 0, 0, 1, and everything else is this coefficient. So that's why I'm writing it as a sum over k state and everything else together. So this sum has gone out. Let's bring this sum over here. So this is sum over x, goes from 0 to n minus 1, and then I have minus 1 power s dot x into minus 1 power x dot k, and I can take sum over k, sum over x, and I can take x common, and I can add these power. So let's take x common and add s, and since all additions are modulo 2, this is x plus k into k. So this is the final state, and let's see what it looks like. And just to give you an idea of different things, let me write it something like c k k, where you can picture it like this. So c0, c1, c2, and so on. So this is what it means, this series. So these coefficients are these coefficient ck's. So let's find out what ck's are. Okay, so this ck, and let me do it for 2 cases. So the case 1 is, suppose, so this ck, let's first write it out, sum over x minus 1 power x dot s plus k. So you see in this sum, this x is changing. It's going from 0 to n minus 1. And then this k is fixed for each of this state. And this s is fixed as well. So s is a fixed bit string, but k could be, since this k is changing for this, terms in the series. So we will have to evaluate this ck for each k. And for each k, I will have to sum over x. So its situation is like this. S is fixed for everything, but I will have to evaluate this sum x for each k. So k is changing, s is fixed, and for each term, there's a sum over x. So let's start doing it. So I can make 2 cases. Case number one is when S is not equal to K. You see, S is fixed, but K is taking different values. K can be 0, K can be 1, K can be 2, and so on. So just to give you an idea again, this X bit string, let's say, is 101, but this K bit string can be 000, it can be 001, it can be 010, it can be 011, can be 100, 101, 110, 111. Okay, for each K, because we have to find this coefficient for each K. And for each of this K, there's a sum over X. Okay, so you see, when K is taking different terms, there are two situations. One is when K is exactly the same as S, and when K is different from S. So let's first take this S different from K. So when S is different from K, and let me take an example. Suppose S is this, but let's say my K is 001. So what this sum would be? The sum would be S plus K is 1 plus 1 is 2. And I have to make it modulo. So this is 0. 0 plus 0 is 0. 1 plus 0 is 1. Now this sum has become 100. Now this X is going to take values from 0 to 1. So let's see now what happens. So this C001 is in the first term minus 1 power 00 dot 100. In the next term minus 1 power 001 dot 100 plus minus 1 power 010 dot 100 plus minus 1 power 010 dot 011 dot 100 plus minus 1 power 0100 dot 100 and so on. So you see, this is the situation. And let's see what this number is. So this is 000 dot 100 and this dot product. So this 00 is for this X, and this S plus K is fixed for a K. So this 00 dot 100 is 0 into 0 plus 0 into 0 plus 1 into 0, all 0. So minus 1 power 0 is plus 1. So this is 001 dot 100. This is all going to be 0. So this is plus 1. So this is 010 into 10. So this is the dot product is 0. So this is 1. So this is 010 dot 100. So this is again 0. So this is plus 1. But this 100 into 100 is 1. So minus 1 power 1 is minus 1. And after this, there would be 100 into 101 into 100. So this will give again 1, another minus 1, another minus 1, another minus 1. So 4 plus 1 and 4 minus 1 will make it 0. And you can actually do this exercise for each of the K that is not equal to S. You will get a non-zero number here for S plus K. And when there's a non-zero number over here, its dot product with all X will give you half of the time 1 and half of the time 0. And you will get a sum of equal number of minus 1 and equal number of plus 1. And all of these coefficients are going to be 0. So in general, these CKs are all 0 when S is different from K. But let's see what happens when S and K are equal. So for the second case, let's say S and K are equal. So if S and K are equal, for example, S is 101, K is 101, then S plus K is 000, because 1 plus 1 is 2. So 2 modulo 2 is 0, 0 plus 0 is 0, 1 plus 1 is 0 again, because 1 plus 1 is 2 modulo 2, 0. So S plus K is 0, which means that since this is always 0, whatever value of X you take, this product is always going to be 0, and minus 1 power 0 is always plus 1. So the sum over X, so CK equal to S is going to be 1 plus 1 plus 1 n times. So this result is n. So it means the coefficient C is equal to n when K is equal to S, and it's 0 otherwise. And so let's go back to this result. So this is CK. So let me write it again. So this CK was 1 over n, sum k from 0 to n minus 1, CKK. Now we have seen that, so this is nothing but C naught 0, C1, 1, all the way to CS, S, and then over here. So this coefficient is 0, this is 0, all coefficients are 0, except when k was equal to S, this is equal to 1 over n. So this was equal to n. So we have n, S, so n cancel with n, and we have S. So it means, sorry, this is not CK, this is psi3. So the state at the output is the bit string state. So now when I measure it, so after measurement, this will give me this secret bit string S. So that's why Bernstein Vazirani algorithm can give you the secret bit string in a single operation. Okay. Is there any question on it? Perfect. So if there's no question, let me stop sharing this. And I think it would be best perhaps if